Right, guys, let's get started. Okay, so let's go to 5:30. All right, so today we're getting very close to wrapping up the whole, like half of the semester is natural language processing, and then the other half is basically like image processing. So that will be, we're going to be switching actually to fast AI, some other tools. There's also a couple of things I need to cover, like kind of miscellaneous little things. But in general, we're doing transfer learning, right? So that's pre-trained models, fine-tuning, pre-training, etc. And so we've started with Hugging Face, we've done language, and then we'll do images. So that's also, it's a whole other area. But so today is probably one of the last lectures on this topic, right? So basically you have your mini projects. Remember that in this class, I don't do a final project, instead we just do mini projects, right? And so you have your mini project, which is the reinforcement learning through human feedbacks, right? So that's what I'm going to spend all of today going over that. I'll go over some of the theory. I will give you some of the papers. Remember, this is a grad level class. It's more of a researchy oriented class. Okay, so I'm going to give you some papers today for you guys to read. Okay, and it's not really like I'm going to give you an exam on the papers or need you to do a summary. It's really read the papers so that you can do the project. You know what I mean? So it's going to be pretty important, but they're very relevant. I will explain the papers today. We're going to kind of like reason about it. And then we're going to go over the code of, once again, if you remember that IMDb, reinforcement learning through human feedback, we're going to go back to it again and kind of, talk about it. So it's really important that hopefully you've started working on that project, right? So I'll kind of talk about it today, but as I'm talking about it, think of the project, right? So you have code that works, right? Remember, you don't need to change the code. That's the beauty of, whereas in 520 or something, you have to write the code from scratch, right? And, you've seen in this class with the GPT that it's not straightforward to write something like that from scratch, right? And that's the motivation is there that we use these transfer learning frameworks. The most famous ones are, as I said, Hugging Face for, although they do vision and other things, there's some natural language component in most of what they do. And then Fast AI, as you will see, mostly images, but they do also do other stuff, right? So it's kind of like everyone wants to, every company or framer wants to address everything, but they have their core strengths. And also there are, in fact, things like YOLO, which is another thing for image detection of object in images. So that's another transfer learning framework. And there's also, actually, PyTorch itself has its own little pre-trained models, right? Like ResNets and things like that you can download as well. So I'll talk about some of those things as we start moving forward. But right now, my goal, especially today, is to kind of wrap this up and to kind of figure out when you guys will do your presentations. But it probably needs to happen before spring break. Do you guys know when spring break is? Like which week? We're currently on week 7 right now, right?
I think it's the 11th to the 16th of March.
So what week is that? Do you know if that's week like 12?
What week are we on?
This is week 7. We are currently on week 7.
Yes, week 10.
Week 10.
Week 10 is spring break. So week 9, that's in 2 weeks. Do you guys think you can do this in 2 weeks, be finished? Yeah, well, we're gonna. Yeah, that's my goal today, right? That's my goal. It's today is literally the mini project. Now I've already addressed a lot of it, and today is just, I'm gonna do what I've been doing with all the scripts, debugging them line by line, kind of give you an intuition. But at the end of the day, remember the problem. That problem was generating text, right? You understand that. You got a little sentence and you finished it about a movie. So what did you think about movie so-and-so? The Godfather. And then it would just say, oh, that movie is really great, or that movie is violent, or something like that, right? That's it. That's kind of what it does. But then you want a model that is even better than, right? I don't know if this makes sense in your head, but this is the trick. Actually, I don't know where ChatGPT is right now, but it's kind of how they did ChatGPT from what people know, right? Just make the answers a little bit better. So for instance, if it describes in that example of the Hugging Face repo TLR, they just wanted to make the movie reviews more positive. Do you guys see that? That's basically the idea. So that's, you know, I'm working on this project where I want to give it a high school math problem. And then I want to get a good solution to that high school math problem, right? But you guys, I'm using that as an example. It'd be great if you guys find some problem that you want to address, right? Think of that. You need to find a data set that has specific characteristics. Do you see that? And then the goal of what you're doing is to generate better text. So in ChatGPT, they would give it a question and they wanted an answer. But the fine tune without RLHF ChatGPT, you would give it text and it would just continue generating text. It wasn't really question and answer. You see, originally, just some text, finish it. But then they did this RLHF where they started to give it examples of things that look like a question and an answer. And then the weights get updated to kind of be able to generate that better answers given a question, the prompt. Does that make sense? This is all you're doing, and all of it happens by changing the weights, basically. Do you see that? So the goal today is I have some, so I'll start, I guess, showing you, we have some papers. All right, I got one paper here and the other paper. So this is I'll add this paper. This is the paper you need to read. It's called Fine-Tuning Language Models from Human Preferences. This is what the TLR library is actually based on, okay? And then the other paper was related to some metrics. Let's go over here. So the paper you need to read, fine-tuning language models from human feedbacks. There it is, by Siegler, 2019. This is how basically this works. You know, when you're doing these kinds of projects at this level, cutting edge, you're basically just having to read the papers, get a feel for how they work. Okay. So you can see this one here. That's basically TLR. Okay. This is what I'm going to discuss today, give you an intuition of some of the ideas. We're going to think of the problem, and then you could implement this from scratch, right? But I'm not asking anybody to do that, right? That would be a little crazy. So OpenAI did that, right? So with a lot of people. Instead, we use Hugging Face, which has created this TLR library based on this mainly. And then you just have to learn how to form your data set so that you can solve a problem, even though you don't get into all the details of the code. Does that make sense, guys? So I will add this link to the mini project. This is one of the papers that you definitely should read, okay? Notice the paper is from 2019, 2020. So it's actually not that, well, I mean, you could argue it's old in terms of this field because it moves so fast, but it's really not that old, okay? So I copied that link. So I'm gonna go to I haven't created the mini project thing. All right, I will add it then. So we're going to start building this up. And like I said, there's no rush in doing this because I really want you to do a good job. I'm like really curious about what you can do with this. But it's not, some difficulty, right? So but I'm trying to like give you everything that you need in order to be able to do it. Okay, so I'm gonna create this as mini project 1. And this is gonna be reinforcement learning through human feedbacks, right? Okay, so that'll be some papers to read. You got the code from Hugging Face. And then there's 2 things that I can't help you with. Those are the things you have to do, right? Which are the data and the reward model. But I'll give you some insights into everything. So I've been dissecting this. And so I think it's very much, I actually ran it again today on the GPU Scholar, and it ran in 40 minutes, which was really impressive. All right, so I'm gonna move this further up. So this is gonna be right. So it should go here. So we did the homework we've definitely done, right? So pre-trained homework, GPT from scratch, you understand all of that. I did provide some links initially of this, and some of these do still apply. Okay, but let's just focus on mini project right now. So one of the things I'm adding here, I'm going to create a link for that paper. I'm going to call it the Siegler paper. So Siegler. And in the documentation, and I'll say 2020, in the documentation of Hugging Face, it says that they basically wrote all that TLR library, kind of following everything in this paper, mostly. Okay, so there is that, okay? So you got one paper, which is essential. Please start reading through this. Okay, there it is. And I'll keep adding more things. So today I'll go over a little bit of theory. Okay, I'll go over a little bit of theory, and then we'll end up just running the code again. I have done like I did before. I've broken down line by line just to kind of print out what everything is doing in the code. Although some of those functions you wouldn't really need to know what they're doing, but just so that we're almost very clear on everything that's going on. Okay. So in the GitHub, I have in the transfer learning one, right? So if you go to the transfer learning one under Hugging Face, 2024, GPU required. These are basically the scripts that I've been kind of breaking. All of these are in kind of like in a sequence to get to RLHF. Okay, that's kind of the idea. So we went over how to fine tune a GPT, right? We did this with Hugging Face. We went over how to fine tune a BERT. We went over that with Hugging Face. Then I have this one, Hugging Face fine tune and load your own data. And we went over these. These are basically the same one, just me breaking down every single one of the lines of code, right? So we've covered that. Now I have, if you notice, this is basically the same thing. Text classification, glue, and IMDb RLHF debugging. So these 2 scripts are new, which is what I was preparing for this week. Hopefully these are like the final thing, okay, that we need. This is actually the code you can use, right, with the TLR library, except that you need to provide it your own data for your own problem, and you need to have your own reward function. All right, so those are the things that we're going to talk about today. Okay. So I will actually start with this one, RLHF debugging, and then I'll come back to this one. So the reason for this is that the data is something you need to collect, right? You need to get that data, but you will need to use a reward function. So the trick that Hugging Face used is that they just use a BERT scorer or something like that as the reward function. So the problem might be then, what if you can't find a BERT scorer for your specific task? Let's say that you were doing like high school math problems, right? There may not be a BERT scorer that can read a high school math solution and say, I give it a score of 1 or 3 or something. So in that case, you may need to train also the BERT scorer. You see that? So that's a second training. And that is actually done through classification. You see this? So this example, text classification, glue, is just code to take a BERT or a GPT and have it predict a class. Do you see what I'm saying? Like happy, sad, and then you can use that as your reward model. Okay. So that's basically the logic here. We have these two, but if you can find a BERT scorer on the GitHub hub, then you don't need to train your own. It's kind of up to you at this point. If you do that, basically write a paper and submit it to some conference, because you've done, it'll be a good thing. And like I said, I don't have it necessarily a rush to get this done in 3 weeks. If you guys are doing good work, right, we can take our time. But yeah, those are the ideas. All right, so today I'm going to go over these 2 scripts at the end, but I do want to start with a little bit of theory first and just kind of to get this ideas in our head, and then we're going to go back to run the script. So I ran these on the Scholar Cloud and they run nicely, right? And as I said, I was very impressed actually. I got an A30 or something like that, and it ran faster than when I had run this on my own GPU. So it can be pretty fast. Does this make sense so far, guys? You have to start thinking about a problem. So I'm going to give you examples of problems, right? Let's start with ChatGPT, the thing that started all of this, right? You've seen how in the pre-trained model, you give it a prompt and it generated some text, correct? And I called it, "Where is Huck?" And then it was terrible. You see what I'm saying? So what they did with ChatGPT is they had a pre-trained model like that. Then they probably fine-tuned it or something. I'm guessing they did fine-tune it a little bit, but that didn't work. So then what they did is they created this reward function where you basically now you'd say, "Where is Huck?" And it would say, Huck is a character. Huck is here. Huck is at his mom's, or well, he didn't have a mom, but at his friends, right? So it produces several outputs. So the trick with this, what they did is they used something called reinforcement learning through human feedbacks. Okay, that technique basically uses what humans think about the outputs to train the model. Do you see what I'm saying? So that's basically what we're going to that's kind of the idea, the theory, right? So that's how then ChatGPT kind of worked, is like it would have a question, generate answer 1, answer 2, answer 3. A human would then look at the 3 answers and say, this is the best, this is the second best, this is the third best. You see that? And it would use that data, which is technically like classification data, labeling data, to improve the GPT, because the weights are going to be changed according to that. Do you see that? That's kind of the intuition of what we're trying to do. You can't build a reward function just by like sitting down with your friends and say, oh yeah, we're going to do it like this, and it's going to give a 1 when this occurs, because it's really hard. It's like the example of the original paper when you have a robot trying to learn how to dance salsa, right? How do you write a reward function that says that's good salsa dancing? But a human can look at it and say, well, I look at this version of dancing and that version of dancing. This one to me looks better. You see, that's reinforcement learning through human feedback. It's basically like saying humans don't actually know how we know something, but we know it. So that's the same thing with this idea with the questions. You give it a question, it gives an answer. So I tell you guys, where is Huck? Huck is eating an apple. Huck is at his friend's house. Huck is a kid. Which one of those is the best one? The second one, right? You just know it. You read the sentence and you just know, right? That's the main concept behind reinforcement learning through human feedbacks, okay? So the idea with you guys is you're going to pick a data set that then you can improve. You could go with question and answers. I'm actually guessing that data set exists, okay? I'm pretty sure a lot of people have tried to replicate what ChatGPT did. So there must be questions and answers and a label. Do you see what I'm saying? And so what you would do is try to go from a model that you give it a prompt and it gives an answer to, or generates text, to one that when you give it a question, it looks, what it gives you looks a little bit more like an answer. And then you can do the same approach as they did in the example, where it would show before, whereas Huck, this is what it generated, and then this is what we get now. And yeah, it looks a little bit more like an answer to a question. Does that make sense? That's it. It seems that's it, right? There's a subtle thing going on there, and that's the project, and you have the TLR data set for it. The trick is, you know, I want you all, I could have said just repeat this, right? But kind of what I want you because it's a mini project, is to have your own data, your own problem. But it's okay if, you know, maybe start looking for that question and answer one, because I'm guessing it probably exists, that data set, and you might want to grab it. Does that make sense? Yeah, everyone clear on what we're trying to do? All right, so let me go over the whiteboard. I'm going to bring up the whiteboard, just give you some diagrams and things like that of some of the ideas, okay? And then, like I said, we're going to get into the code and break it down. But it's a lot, the code, the reason why I did all of, oh, okay, I have them here. So I did all of these because if you notice, I don't know if you noticed, but all of these are from Hugging Face, and they're all kind of using the same concept of a trainer, if you remember that. So there was always a trainer, right? There was always a trainer to train the BERT, the GPT. There's a trainer for the classification. There's that collator thing, right? And then now there's going to be a trainer called PPO.trainer. And this PPO trainer is the RLHF trainer, if that makes sense. But it's going to be consistent with what you've been, with what we have seen in the previous examples. Does that make sense? All right, so let me now bring up the whiteboard. And let's just kind of like try to just, you know, kind of like reason this, all right, in our heads. That's really what we need to do, right? Reason this out. And I've read this paper, the Siegler paper, so I'm going to steal some things from there for the lecture, but basically to kind of like illustrate, right? Now, a lot of this you don't have to do because that's what PPO trainer does for you, right? But I want you to understand, you know, what's going on. Okay. All right, so I've got the whiteboard there. All right, so again, the idea is we have a GPT. So this is definitely the model that we're training. However, there is another model, at least in the I'm going to refer to the IMDb example. They actually created the reward function based on a BERT model, a BERT scorer, okay? So this is the reward that they were using, but really the model that you're trying to create, the one that you would go and sell to the world, is this GPT, not this one over here. Do you see that? That's basically the idea. You guys already know, and I'm not going to go over theory anymore, but you give it text and it generates text, right? That's it. So you're still doing this. Probably use GPT-2 unless you want to use Llama or something like that. I encourage you to try whatever you can and use all the resources available. So basically, you know, we have seen where is Huck, and it gives you some text. So we've got text here and it generates text, right? But it's just not very good for specific tasks. Now we're taking it to like, okay, I have a pre-trained model that just generates text, but I really want a model that can do way more than that. Like I give it, you know, a question, and I want something that looks like an answer. Do you see that? Still within the fact that given some text, it generates text. So the way to do that is you don't really change the structure of the GPT at all. What you're going to try to do is change the weights inside, right? That's the only thing that you do, right? So this is how no one has really tried to change these transformers. Since 2017, when they were created, they're pretty much the same thing. No one has like gone in there to mess with them. Instead, everything that is done is based on outside, like treating it like a black box, and then what are the techniques that we can use to make it better. Okay, so obviously we give it a sentence, it generates a sentence, but I want this now to be a question, and then I want something that looks more like an answer. How do you define that? I don't know. Nobody knows. No, they even said that, right? I don't know. But the trick is, what if we take this idea? Now, this is the GPT. So I give it a question, question 1, and I'm going to have it generate 3 answers. Answer 1, answer 2, answer 3. Do you see that? That's the trick. So now you say, okay, while I don't know how to tell it what a good answer is, I can have some humans who are intelligent and trained for this, and they will look at these 3 answers and say, I like this one more than this one than that one. Do you see that? And just that alone is enough to create a data set that can be used to further fine-tune the GPT to be better, because now the weights are going. So let's imagine that you have this feedback, right? So now you repeat the task and you're updating the weights every time. So you try one set of weights and it generates an answer. And now that it's gonna basically compare those to the scores. So that's really the idea that we want here. Okay, so it's gonna generate an answer, and so you have something like that, and you need to assign a score to it. Okay, that is closer to 1 and not close to 3. Okay, so that's kind of what we're trying to do here. Okay, so let's think a little bit about this. All right, so how did they achieve this? So the basic idea in the RLHF is something like this. You have some text, you have a GPT, and this GPT generates some text, right? Then you need to have a way for this text to become a score. You see that this is a number, right? This is a number, like from 1 to -1. Do you see that? How is this accomplished, actually? We don't even need the text here. We can actually just take one of the previous layers, which is an embedding. If you remember from the encoder, right? The last layer of the encoder is just an embedding, a vector, that vector, embedded vector. So you actually don't even, although it would, in the next layer would generate this, you can actually just take this one. Do you see that? I'll use a different color here. And then basically you connect that to this, okay? And this layer here is what? It's a feed forward, fully connected linear layer of some size. And then this final vector here would be the score that you're trying to predict. Okay? So the idea is you need to have some kind of a loss function here to minimize this, right? So that means that you need to have some data with a score. So now you're going to have some text. And this text generates other text, right? Just like the GPT, imagine this is a this is a question and this is an answer. Do you see that? So it's text generates some text. And you give that a score. But this is the trick here. This is the human feedback. So that means this is done by a human. Do you see that? That's RLHF. So basically the idea is you need a data set where people have read questions and answers. So they read this question and this answer, and they said that question and answer. Where is Huck? Huck is a river. 0, right? That's the score. Then that a human did that. Then you have another one. Where is Huck? Huck is at his friend's house. What score do you give that? 1 or something. The human does, right? Really high score. And now what you want is you want the GPT model to also learn to do that. Does that make sense? Any questions on that? That's RLHF right there. Okay. So that's the basic idea of it. And so it's a clever idea, right? Because you know, you have a GPT, the weights are being changed, you know that the text is gonna improve, you know, it's almost like if this is a 1, then the text that comes out here is Huck is at his friend's house. And if it assigns a 0 to it, then this is Huck is a kid or something. So it's a bad output given the input. All right, so that's what the model needs to learn, basically. Question, yes, please.
So like in regular, like when you're training a model, you have, 80-20 for testing and training.
Mhm.
So in this situation, how, like, is there a current standard for like how much human feedback data there should be?
That's a great question, actually. So in the Siegler paper, they did 2 tasks. They did summarization and they did something called completion, I think. I can't remember exactly, but 2 tasks. In one, they use 5,000, and in one, they use 60,000 examples. That's it. So pre-training requires all the text in the world. Fine-tuning, 100,000 samples. RLHF, probably even less. So it is believed that ChatGPT was trained with just 100,000 question and answer pairs that were human, that were high quality for humans. Like the data set that I'm working on right now of high school problems and high school answers is only 8,000. Yeah.
But like how many, like, so in this scenario,
Yes.
you're having like a literal human generate some of the data.
Yes,
How
definitely.
much of the data should be, like, what percentage should be human generated so that the GPT can properly learn how to make those scores itself? Like, is that a thing yet?
Well, that's what I just said, like 5,000 to 60,000. Is that what your question was?
Like, do you mean 5,000 is like the entire data set?
Yes, the entire data set.
How much of that data set is human generated?
50,000. No, those 50,000. Well, what I said, 5,000 examples in the Siegler paper and 60. I remember it for the summarization is 60,000. I'm pretty sure.
Okay. Okay, that is.
But yeah, so it doesn't need to be big.
Yeah.
And like I said, with ChatGPT, I understand it was 100,000. So it's like a question and an answer. And this is really high quality data that it needs to learn from. Do you see that? Any other questions? So there's various ways that this can be done, but initially this was done as have the model in real time, give it an input, generate an answer, and then have a human look at it and give it a score. Then give it the question, generate another answer, have a human give it a score. That was done like that. And that's a good way of thinking about it. But you can have other ways of thinking about this, like generating a question and an answer and making it really good and giving it a 1. And then generating a question and an answer that's not so good and giving it like a 0.5. Do you know what I mean? You can create whatever you want, but it's all like has to be human judged. That's the key. Whether you use automated things, like that's possible, right? You can have a GPT, give it a set of questions and generate many answers to it and have a human score it. What's important is the score. Or you could have like humans literally craft both the question and the answer and just have high quality ones. And then probably I would assume you need to have some lower quality ones as well. Joey, do you have a question?
Yeah, the score.
Yeah.
What goes on for that? Can it be, like, you have 1 and -1, so should it all?
I use that as an example.
Right, so should it all be, would normalizing it be better? Or like, can we just do 0 and 1 and like a Boolean?
Yeah, Yeah, you can try whatever you want, as long as there's a score there that indicates difference of something.
Okay.
It's basically, this is just a classifier, actually. So it's not even a regression model. If you think about it, this is the other thing I was saying. So in the IMDb example, right? In the IMDb example, right? They use a BERT classifier, actually. Not even a BERT regression model. It's just a classifier of positive or negative. So what that BERT does, right? That BERT takes in an input, which is text, right? Of some kind. Now, this could be the question and the answer just append or concatenated to each other. I believe actually that's how they did it. And then this just says positive or negative. Do you see that? It's really a classifier that they used in Hugging Face, but they don't use the labels. See, this is a thing that we know from machine learning, from deep learning before, right? Let's think of iris as an example, the iris data set, right? So we've got 1, 2, 3, 4 as input. Let's say we have one hidden layer of 6, 3, 4, 5, 6. And then we have what? 1, 2, 3. The three classes that we have in iris, setosa, virginica, and versicolor, right? Similar to pos or negative. But if you remember, what we get here is a softmax a vector of logits, right? So we got the logits here, and they are softmax, right? So do you remember what that means, right? It means that we actually get what? 0.2, 0.3, 0.5. They add up to 1, right? And usually how do we select the label? We select the label of the ID, or we select the ID of the highest value, correct? So in this case, 0, 1, 2 would be the labels. We select 0.5, so we get class number 2. Do you see that? That's how a classifier works. And this is something you guys know. Well, that's what they did actually in the Hugging Face thing. They didn't use the pos and negative directly. Instead, they used the score here. And effectively, they converted that into a reward function, even though it's just a classifier. So the beauty of this is you can train this as a classification problem, label it positive, negative. Take a sentence, positive, and sentence, negative. But by the nature of deep learning, if you don't take this step of taking the index and just concentrate on this, then you use this value as the reward to the model. And that's how they did it. So that was really clever because it makes it easy to train as a classifier, but then we have the reward function. Any questions on that one? Making sense? All right, so yeah, so these are the tricks, right? So this is basically the idea. So we want a GPT model here, right? And it's got some text prompt, get the answer or whatever it is. It's got some weights. This is the embedding. The embedding would then be converted into the actual text itself. But we actually can be clever because if we went with the text here, that means now we need something else to read this text, reconvert it into embeddings, and do all the processing. Instead, what they did is they just take just the layer just before where you convert to text, the embeddings, and they tied that to just some feed-forward linear layer. And this, remember, it's almost like the example, remember, where I did like everything was frozen and then this was unfrozen? So that's kind of the idea, right? You have this frozen and then you have maybe this layer, which is where the weights get updated to score, right? But I'm sure they do more than that. That's just an example. But the idea is they map this to this. This is, you probably have to update all the weights. But this is just a connecting layer between this and this, okay? And so in this example, this would generate, as I said, imagine this is just a neuron generating values from, let's say, 0 to 1 or something. And then you need to obviously have values here from 0 to 1, right? Does that make sense? The idea being that you have this model to change the weight so it can produce things that look a little bit more like this. Now, that's the theory of the original Siegler paper, but you guys don't need to implement all of this, right? Instead, we're going to leverage the TLR library to do this for us. But you do need the data, and you do need to figure out some kind of a reward function. Making sense? Any other questions? All right, so let's kind of summarize then. So when you read that paper, there's going to be, so you have this, so you have 3 steps, right? So the training process, you have the data, you have the model. We've got text, GPT, the embedding, the text itself, the feed forward, and then finally the score value that you're predicting, the logic, you could call it, right? And then over here you have text, human, text. They read this and provided also a score. Okay, so this loss is kind of like the thing I'm going to mention just briefly. So this loss function, basically, it would need to minimize these 2 values, right? So that it predicts the same thing. So that's the idea. So that's the 3rd step of this, the loss. But it's got 2 parts, okay? So that's the only thing. There's basically like saying there's going to be a model, the GPT that you're trying to modify, and there's going to be a second GPT that you're going to see there called a ref or reference GPT, okay? So why do you have that? So the idea with that is that you don't want, as you're giving data to this GPT, the weights could be changed like very aggressively. You see what I'm saying? Like they could become very different weights very quickly. And so what they wanted this GPT for the weights of it to change, but not so dramatically. And so that's why they keep like the original GPT, and then they have this one that is changing. And constantly they're comparing those 2 GPTs so that the weights don't become too different or too pronounced in the difference. Does that make sense? And it's kind of like a distance function. Okay, so basically we can say, so I'm gonna just continue in the next page. All right, so remember, you're gonna see this in the code. So there's a GPT and there's gonna be a GPT ref. This one does not change. It's the original one. During training, they're going to compare this GPT to the GPT ref to make sure that the weights are not changing that much. And that is done through a function called the KL divergence, okay? So it's something from information theory that looks at the distributions of things. So we're not going to get into the details of that, but just be aware that that's the reason why there are 2 models in there, okay? So it's like a thing where it's like not letting it change too much, okay? So that's this technique. So then the loss function that you saw is not just about minimizing the score that's predicted versus the score that's real, but there's also this additional component. So usually, like if you think of MSE, right, or something like that, mean squared error, what do we do usually with MSE? MSE is usually what? Y hat minus Y squared, right? You guys remember that. That was the loss function, right? We're kind of doing the same thing here, although we're using cross entropy, but we're doing kind of the same thing in minimizing the scores. So it's a similar type of a loss function. However, there is this additional component here, multiplied probably times some parameter. You'll see that in the paper. And it is this called a KL divergence, which is basically it's taking the GPT that you're updating and always comparing it to the unchanged GPT to make sure that the weights don't go like crazy out of, and that's basically it. Okay. So as I said, you don't have to implement any of this, but that is in there in the paper. Okay. If time permits later on, I will give you a simple example of how KL divergence works, but with simple data, not with like the GPT data. Okay. But that's it. So these are the three components that the Siegler paper will talk about. The data, the model as you see here for training, and then this loss function, okay? So definitely read the paper. I added the link. As I said, it's called Fine-Tuning Language Models from Human Preferences from 2020. It was done at OpenAI. This is the paper that Huggin Face used to create the TLR library that we're using for this class, okay? Make sense? Any questions? Yeah, go ahead, please. No, I'm sure it's great.
That the score update, like when you come up with the score, the weight updates. How does the weight update? Like, is this like a
Back propagation? It's back propagation. It's the same way that weights update before.
I think I just never like, that's one thing that's always escaped my brain. I'm gonna look into.
All right, so no. It's all neural networks. These are like huge, incredibly long, deep neural networks. But it's a neural network. So it's how does this work? Input, output, right? Oops, sorry. Input and output, right? And in between, you can have one layer or like 128 layers, however many. A transformer is in there, right? So you give it some data, it goes through here. All of these are just transformations. That's all it is. And at the end of the day, you get your output. For Iris, just classic example, 1, 2, 3, 4, correct? We give it a feature of 4. What do we get over here always? A vector of 3. The logits, because it's a classification. But remember, the neural net doesn't say, oh, it's a setosa. It'll never say that. What does the neural network say? For Iris, it gives you a soft-maxed vector of 0.2. Well, actually, they're going to be probably really good, like 0.2, 0.2, and then this one would be 0.98 or something for a really good model. That's what it always gives you. But then what do? The same thing I was doing before. You take that vector. Only the thing is, this one is 1. There's no decimals there, remember? And what do? You compare the two in a loss function, you minimize. Do you see what I'm saying? So you do the forward part first. Go in there, produce this vector. That's the pred, the y pred. And then this is the y real. So you're going to compare these two, like take the difference. So just in the example of MSE, you take y hat minus y, square it. This gives you a result. For a given set of weights, that value could be 0.7. For another set of weights, that value could be 0.01. Which one of those is the best one? The one that gives you 0.01. You see that? That's the minimization. But the trick is, so I always tell this students, right? So how do we, that's optimization. So I could try, let's say I had a quantum computer. So I can try all the sets of weights in the universe and at once get all the predictions, compare it to all the reals. The one that gives me the lowest loss, that's it, done. But we don't have a quantum computer where we can compare all the sets of weights. So we need to do it in an intelligent way. We need to know how to do it. So there's an algorithm called backpropagation that it takes this information, like whatever this value was, let's say 0.3, and it's gonna use that to decide how to update these weights. So the weights would be these ones, the ones that connect here. It's gonna, it needs to do it for every single one of them, okay? Because remember, you have now a number, right? You produce this, you compared it to the real. So these numbers that you calculated, 0.3 or whatever, that's what backpropagates now. I'll change a color here. So you backpropagate that information to update the weights. And that's an algorithm, like, you know, uses calculus. It's that whole idea. Do you remember?
Do you mean like when it's updating the weight, like it's using an algorithm?
Yes, when it's updating the weights, this is what Geoffrey Hinton invented that made him like the most famous person in AI. How to backpropagate. Why is it called backpropagate? Because when you predict these values and you compare it, the predict to the real, you don't have information here, correct? It doesn't work that way. Where do you, the only place where you have information initially is here, because you compare the predicted to the real, took that difference based on some loss function, and let's say it gives you 0.3. So it's called backpropagation because this data needs to now backpropagate to all the layers, but it doesn't do it instantly. It first needs to go layer by layer. So it's gonna use that 0.3 to change the weights. And then once the weights are changed, it updates these values. And then these values become, let's say 0.2, and it's gonna use that information to update these weights. Oops. And then this one becomes 0.4 or something like that. And that information is used to update these weights. So that's why it's called backpropagation. Back just means going back, and propagation is that it's doing it layer by layer. But the information starts here at this 0.3. Do you see what I'm saying?
No, it makes, I do understand that. I think there's just like a black box in my head for like, so like you say like the 0.2 is the weight per se.
Well, not the weight. It would be the weights need to change based on this. And then once you have this data and these weights, you can get this data. It's almost like this, okay? So if I have X here and I know the weights, I can predict hidden one. Do you agree with that? Like I have this data, right? Some numbers here and I have these weights, boom, I can predict this. So that's going forward. Going back is the opposite of that. So now when we get to the end, so this is real data and this is the pred data, right? So I get a number here, something. And that number is the equivalent of, in the last layer, now I have values here. I update the weights. I had original weights there. I'm just going to update them based on this. There's an update rule, okay? And that update then gives me a new set of weights plus this, and now I can calculate this layer because I'm back propagating. And then I do the same thing. Here I have another set of weights, but I'm going to update them based on this. And once that's done, I have this and this, so I can calculate this layer. And so you're back propagating the information. Initially, you were going forward, now you're going back.
Yeah, no, I feel like the question that I'm asking is, I'm just maybe not like phrasing it properly.
Yeah,
Like,
what-
I understand what the back propagation is, but
Yeah.
like, when you, like, at the actual weights, when you are literally doing the update to it,
Mhm.
are you multiplying, like, what are the rules? What are you doing from taking the basic, like, original weight? And like, how are you changing it?
Oh,
Making a
okay.
new number? Like, is this like a matrix multiplication?
It is a matrix multiplication. So let's go to, I have an example here.
Sorry if I.
No, that's okay. That's okay. Hopefully I can answer it. Let me try. Let's go to the book. All right, so if we go to, I think it's here, chapter 2. Like I said, I should have an optimization here. Here. See that? This is what we're doing. And this is the actual update that you're asking about.
Okay. That, yes.
Yeah, so basically here you have an old weight and you're going to modify it in some way. But how do you modify it? Really, there's two things there, right? You remember the learning rate that we talk about the learning rate all the time? Well, the learning rate is really, let's think of it as this little value here, step size. Notice I just called it 0.01. So what the learning rate means is you take the weight and you're going to modify that weight by that learning rate, either up or down, right? So by default, you can just use minus or plus here, just be consistent. The question is really, the problem is that part. Do you add it or do you subtract it? Do you see what I'm saying? So so basically you have the learning rate already because you defined it initially. You're gonna do this for all the weights. So this has to be, so it's probably a matrix multiplication of that whole weights matrix times something, right? Because you need to modify all of them. But the question is, what do you do? So here you are gonna multiply that step size by the result of this function. And what is this function? This function is like the definition of, we have to use calculus here. That was like the inside of it, right? And the best way to kind of understand that is here. Okay, so this function here, going back to the loss function, what does this curve represent? It's a function, right? Do you remember the function that describes a curve like this? Squared, x squared. It's a quadratic function, basically, if you remember, right? So if I have 0, I'm at the bottom. If I have 1 or -1 squared is still 1, right? So it goes like that. If I have 2 squared, 4. If I have -2 squared, still 4. So it's growing like a thing like that. What function looks like this? MSE. Because it's y pred minus y real squared. If you look at y pred minus y real, really just x. And it's x squared. So it's got that shape. Okay? If we were using cross entropy, it gets a little bit more complex, but it's still understandable. Okay? So what you need to understand is that the loss function governs basically a relationship. Okay? The loss function governs a relationship. So you're going to find yourself doing that back propagation at some point, right? And you're going to plug in this, you're going to use this W to predict something and compare it to the real, right? And because you're using the quadratic, it's going to put you somewhere on this curve. So in this example, for instance, it's going to put you right there. See, this is the W, right? The weight, where it is. So if you plug it into the MSE, the MSE is almost like, just imagine it's a space that is a curve. So wherever you are, it's going to put you there. So in this case, it put me right here. My goal is to, if you look, this is the W versus the cost. The goal of this is to minimize that cost. That's why the loss function is about minimizing. So you want to get this to be the lowest. So when is it the lowest? When it reaches the star. Do you see that? That's its objective. So what's great about this is that in calculus, when you have a function and you have parameters and you take the derivative of that function in terms of that parameter, you calculate something with the derivative called the tangent of it. And that value that you return, that returns, is basically this tangent. If it's here, let's say it's going to be positive. If the tangent were on this other side, it would be negative. And so that's the symbol that you need to use to go down to the loss. Do you see that? That's basically the whole logic of it. So as you get some values and you start to backpropagate, you're performing this hundreds of thousands of times. And this is why it wouldn't make sense to do it sequentially because it would be too slow. So they do it through matrix multiplications. But this is what's happening.
That makes so much sense.
This makes sense?
Yeah. For some reason, my brain just could not comprehend that before.
Make sense for everyone? Now, I added here another example. If you notice, this is, I didn't use the quadratic. I just used like a normal function. But imagine this is your loss function, right? That would be the MSC original. Then you would always take the derivative of it. So the derivative of this one, x cubed minus 3x2 plus 7 is 3x2 minus 6x. So that's the derivative of it, right? And the key thing there is that this function then is basically this one. Do you see that? Because I wrote it here, you see? 3x is basically this 3x, so it's already there. I had to do this manually. PyTorch does not do that, right? PyTorch will start here and it calculates the gradients. So do you remember when we looked at PyTorch code? There's what were the three infamous lines in the loss function? It was zero out the gradients, then loss something, and then step, right? Step is the last one. I can't remember that. There's three that are happening, right? One of them, the one in the middle, lost something. Lost out backward. There you go. Thank you, Joey. So that's basically what it's doing. It's calculating the derivative. So it's going to take that MSE or cross entropy, boom, get this one. And that's what it's going to use with the value to return either plus or minus, which is basically the gradient here. And that's how it updates. But it does it for every W individually. Okay, that's what's called calculate the gradients and all that. That's how it works. This is literally what Jeffrey Hinton and his team invented in 1986. Okay, and it's the only technique, by the way, that makes everything in deep learning work. There isn't a second one. There's only one, and it's this one. Makes sense? So I wrote this derivative in there just to kind of for like educational purposes, but just keep in mind, this would be automatically calculated by PyTorch. That's actually why we don't use NumPy. So NumPy can do a lot of it, right? Then why not just use NumPy directly? Because NumPy does not do these derivative calculations. That's done by PyTorch or TensorFlow. That was the thing that requires us to use their frameworks. Yeah, all right. So if let me just kind of, if I go to in chapter 4, this is actually where we're using that was for MSC, right? I don't know if you remember that for cross entropy, we basically had another set of equations for the loss. This is here. Yeah, these are for classification, the equations, okay? Instead of MSC. But what's important about these equations is, notice that you plug in the W times the X, and that becomes what goes into the loss. So the W is somehow connected into the loss. You know what I mean? Even though in the picture I only showed W, remember W goes into the function with X plus B, produces a Y minus a real, and all of that gets optimized. So what the function does is at the end of the day, it governs the relationship between this W and the output of it. So it's the same thing here. Here you have this HX, which really should be like the W is included in there. It's the way that I wrote it. See, I just, if you notice, GWX, right? And then that I made that H0, but it's just a way of calling that function. But I'm still ultimately, to get to this, I still need a W, okay? So whatever that W is that produces that H is this value here. And so the losses here basically control the relationship ultimately through this function between the W's and the cost. And so the cross entropy basically just says that when the real data is, the real label is Y, you use this function. Why? Because this function becomes loss of 0 towards 1. And when we use real data, real label of 0, we use this other function because when this tends towards 0 on this side, then we minimize the loss. You see, that's just the same idea. So you can these functions, you can take the derivatives of them, and ultimately you just get that symbol that updates the weights. That's it. Did I answer your question? You think so? Okay.
Thank you.
I hope I did. I don't know. All right, but anyway, maybe you guys need to code that. All right, anyway, so going back to where we were, I don't even remember what brought this about, but let's go to the whiteboard. Yeah, so I think we were here, right? So we were summarizing this. The RLHF, basically we have a transformer or a GPT gets some text, produces some text, but now we have this additional idea of producing a score. And this score is going to be compared to humans looking at text and you know, like a question and an answer and giving it a score. Then this is during training, you create a model that minimizes this error, this loss, and that's going to update the weights of the GPT further. Okay, so remember, a GPT at the end of the day is just these weights, right? All these weights that are there, and you want to basically update them a little bit more so that the answers are just a little bit better. Think of it as a correlation of GPT weights equals some text that comes out. So if we change these weights in some way, the text may be better. If we change them in another way, the weights may be worse. Or sorry, the output might be worse. So what you want to do is figure out a way to change the weights in the GPT so that we get the text that we want, given the output text that we want, given the input text that we want. Okay? All right, so hopefully that made sense. Definitely read this paper. Okay, and it's 6:17, so actually this might be a good stopping point. I'll check my notes for the theory, but if we're done with the theory, we can move on to the coding part and just try to use Hugging Face once again, go over all the details. All right, so I'll stop the recording here and we can start again at 6:28.